Far beyond the familiar stars of the Milky Way, the universe is filled with vast gatherings of light that from a distance can seem quiet, balanced, and almost serene. Each galaxy appears as a remote island of stars, suspended in darkness and separated from the next by enormous reaches of space. In broad view, they seem graceful. Some spread their arms in slow spirals. Some gather themselves into smooth, rounded glows. Some stretch into thin disks or soft ellipses that appear almost motionless against the black. At first glance, the mind is tempted to sort them into simple families and leave them there, as though the cosmos prefers order and repetition. Yet the deeper astronomy looks, the more that calm surface begins to loosen. Behind the soft light and distant symmetry lies a world of disturbance, hidden structure, and long unfinished change. A galaxy is never merely a picture. It is a physical system of stars, gas, dust, dark matter, magnetic fields, radiation, and motion, all held together and reshaped over immense spans of time by gravity. Even the most ordinary-looking galaxy carries a history too large to see all at once. It may contain regions where new stars are still forming inside cold clouds. It may carry ancient populations of older stars that have been orbiting for billions of years. It may hold the remnants of smaller galaxies drawn in and dissolved long ago. It may even hide unusual motions or invisible matter that cannot be seen directly, but can still guide everything around it. When these possibilities are kept in mind, the distant glow of a galaxy stops being a static object and becomes a living record of change. This is part of what makes the strangest galaxies so compelling. They do not simply decorate the universe with unusual shapes. They reveal, more clearly than quiet examples often can, the deeper rules and tensions that govern cosmic structure. A galaxy with a broken arm, a bright ring, a dark scar, or a lopsided body is not merely odd in appearance. It is often exposing some event, force, or imbalance that more regular systems hide more gently. The strange cases make the underlying processes easier to notice. They turn hidden physics into visible form. They show that the universe is not content with a few neat patterns repeated forever. It allows collision, theft, compression, distortion, revival, and sometimes arrangements so elegant or so chaotic that they seem almost designed to challenge expectation. From the outermost perspective, galaxies are among the largest coherent structures in the universe that can still be thought of as single systems. They gather anywhere from millions to trillions of stars, along with clouds of gas and dust that can drift, collapse, heat, glow, or be blown outward. Around and through them lies the far greater presence of dark matter, unseen but inferred through gravity, shaping the paths that visible material follows. These systems do not float in isolation as often as they appear to. Many belong to groups or clusters where neighbours tug on one another over time. Even when separated by great distances, galaxies can influence one another through repeated close passes, gradual accretion, or eventual merger. Seen in this wider setting, a galaxy is not just a destination in space. It is part of an environment, part of a history, and part of an evolving web of matter that stretches across the cosmos. The oldest light from the farthest galaxies also reminds astronomy that to look outward is to look backward. Because light takes time to travel, a remote galaxy is seen not as it is now, but as it was when its light began its journey. Some are observed from eras when the universe itself was younger, denser, and less settled. This adds another layer of strangeness. A galaxy may look unusual not only because of its own local history, but because it belongs to a different stage of cosmic history altogether. Some of the most distant systems appear to have formed structure earlier than expected. while others show intense activity that suggests the young universe was already capable of great complexity. So even before any specific strange galaxy is named, the subject already opens into something larger than a gallery of odd shapes. It becomes a way of seeing the universe as a place where order and surprise are always interwoven. The broad categories used in textbooks remain useful, but they are only a beginning. Real galaxies drift beyond them. A spiral can be warped. An elliptical system can hide dust and swallow debris. A quiet disk can suddenly flare with new star formation if fresh gas arrives. A faint, diffuse object can contain far more mass than its dim light suggests. A system that looks calm in ordinary images may reveal counter-rotating material when its motion is studied closely. And some galaxies seem so thin, so ringed, so wounded, or so ghostly that they almost appear unreal until repeated observation confirms them. Strange galaxies matter because they remind astronomy not to confuse familiarity with completeness. The universe often keeps its most important lessons inside exceptions. The odd cases teach how gravity sculpts, how matter falls, how stars are born, how galaxies grow, and how visible light can mislead when hidden mass and hidden motion do most of the work. From this far outward view, the first impression is not chaos, but breadth. The universe allows many ways for a galaxy to exist, many ways for it to change, and many ways for it to carry evidence of what has happened to it. The calm glow seen from afar is only the surface. Beneath it lie collisions unfolding over ages, dark halos holding luminous matter in place, central engines bright enough to outshine billions of stars, and structures shaped by both violence and patience. The strangest galaxies stand out because they bring these hidden realities closer to sight. They are not mistakes in the sky. They are some of the clearest expressions of how the cosmos truly works. Among the strangest galaxies in the universe, some draw attention not because of their stars, but because of the astonishing brilliance concentrated at their centers. This seems wrong at first. The central object in these galaxies is often a supermassive black hole, and black holes are known for trapping light rather than releasing it. Yet the black hole itself is not what shines. The great brightness comes from material falling inward. Gas and dust near the center do not simply drop straight down and vanish. They collect into a rotating disk around the black hole, and as friction, compression, and gravity work together, that material is heated to extraordinary temperatures. In that state, it begins to radiate intensely across the electromagnetic spectrum. The center of the galaxy can then become so luminous that it rivals or even outshines the combined light of the stars around it. This is one of the first great reversals that strange galaxies offer. The darkest objects in the universe can become the cause of some of the brightest regions ever observed. When the activity is especially intense, astronomers describe the central region as an active galactic nucleus. In the most extreme cases, it becomes what is known as a quasar. A quasar is not a separate kind of object floating alone in space. It is the active heart of a galaxy, whose central black hole is feeding at such a powerful rate that the surrounding light overwhelms almost everything else in view. This means that when a quasar is observed across vast cosmic distance, what is often being seen most clearly is not the galaxy as a whole, but the energy released by matter in the final stages of falling toward its center. The scale of this process is difficult to absorb. A region smaller than the full spread of the galaxy can dominate the appearance of a system that contains billions of stars. It is a reminder that in the universe, size and influence do not always match in ways that human intuition expects. A central engine can visually overpower the far larger structure that surrounds it. This concentrated brilliance tells a story about gravity under extreme conditions. Gravity is often imagined in simple terms, as a pull that draws one mass toward another. In an active galaxy, that same rule creates a far more dramatic result. Gas clouds drift inward. Angular momentum keeps them from plunging directly into the centre. Instead, they form a disk and spiral gradually closer. As they do, they rub, compress, and accelerate. The energy released in that process becomes light. In a very real sense, gravity is being translated into radiation. The visible effect is not merely a point of brightness. It is the record of matter being forced into one of the most demanding environments in the universe. There is something deeply strange in the contrast between the calm outer shape of a galaxy and the violence that may exist at its core. From afar, the galaxy can appear stable, elegant, and even gentle. Yet inside, near the centre, matter may be heated to extraordinary temperatures, charged particles may be accelerated outward, and magnetic fields may help launch enormous jets into intergalactic space. Some active galaxies produce jets that extend far beyond the visible body of the galaxy itself. These jets are made of particles moving at enormous speed, guided along magnetic field lines from regions close to the black hole. They can pour energy into the surrounding environment and affect the future of the galaxy by heating gas that might otherwise cool and form new stars. This means the central activity does not stay confined to a tiny point. It can reach outward and alter the development of the entire system. The galaxy is not only shining from within, it is being regulated, disturbed, and shaped by its own centre. What makes this so compelling is the reversal of scale and expectation. A black hole is often imagined as an endpoint, a place where matter disappears and activity ceases. But in these galaxies, the black hole becomes the source of observable drama. The feeding process transforms invisibility into spectacle. The centre becomes brighter than expected, more dynamic than expected, and more influential than expected. A quiet disk of stars can contain an active core that turns the whole system into a beacon visible across billions of light years. This helps explain why active galaxies have played such an important role in astronomy. They allow observers to detect objects at immense distance, which means they also provide glimpses into earlier chapters of cosmic history. Light from very distant active galaxies and quasars began its journey when the universe was far younger than it is now. Their existence reveals that supermassive black holes were already present and already growing in the young universe. That fact remains one of the striking features of modern cosmology. It suggests that black holes and galaxies have been evolving together for a very long time, each influencing the other. The strange galaxy with a brilliant centre is therefore not only an oddity in appearance, it is evidence of a deep connection between the growth of galaxies and the growth of the massive objects buried inside them. Not all galaxies are active in the same way or at the same intensity. Some have central black holes that are comparatively quiet, feeding only weakly or not much at all. Others seem to pass through phases of activity, brightening when enough gas becomes available and dimming when that supply declines. This means that an active galaxy is not necessarily a separate family from an inactive one. It may be a familiar galaxy caught during a more dramatic chapter of its life. That idea adds another layer of interest. The strange active galaxy may not be fundamentally alien. It may simply reveal, in a heightened way, what many galaxies are capable of under the right conditions. The brilliance at the centre is therefore both exceptional and instructive. It shows what happens when gravity, matter, angular momentum, and time combine in a concentrated region. It also warns against trusting appearances too quickly. A galaxy is not defined only by the light of its stars. Its deepest story may be unfolding where starlight is no longer the main actor. In these extraordinary systems, the central black hole does not merely sit in darkness. It reorganizes the visible character of the whole galaxy. the galaxy becomes a lesson in how something hidden can dominate what is seen. The farther astronomy looks, the more often this lesson returns. Strange galaxies reveal again and again that the most powerful forces are not always the most obvious at first glance. Sometimes they are concealed at the centre, turning falling matter into fierce light, and making the heart of a galaxy blaze with a force that transforms the entire system into one of the brightest and most unforgettable objects in the universe. A galaxy can reveal its history through shape long before any instrument measures its motion or composition in detail. From a great distance, the outline alone can begin to suggest that something unusual has happened. A disk may appear bent, an arm may seem stretched too far, a bright ring may surround a quieter centre, one side may look heavier than the other, or a lane of dust may cut across the light in a way that feels out of place. These are not decorative accidents, they are the visible consequences of structure, motion, and past disturbance. This is why the strangest galaxies often feel so memorable. They do not merely differ from the familiar spiral or smooth oval. They seem to carry clues openly on their surface, as though the events that shaped them have left marks that never quite fade. A galaxy that looks twisted or scarred is often behaving like evidence. It invites the mind to ask what happened here, not in a dramatic human sense, but in the slow and physical language of gravity, gas, and time. The traditional picture of galaxies begins with broad categories. Spiral galaxies show rotating disks and curving arms. Elliptical galaxies gather their stars into more rounded, smoother forms. Irregular galaxies resist both patterns and seem more chaotic in outline. These categories remain useful because they organize many of the largest visible differences, yet real galaxies often refuse to remain fully inside them. A spiral may be warped, as though its disk has been slightly bent by an invisible hand. An elliptical system may contain dust and embedded structure that complicate its smooth appearance. A galaxy that seems regular in one image may appear deeply disturbed in another wavelength, where gas and dust expose a different side of its condition. This is why strange galaxies are so valuable. They reveal that classification is only the beginning of understanding. The visible form is not a label alone, it is a record of process. When a galaxy appears broken or asymmetric, the most likely cause is often interaction. Gravity does not need direct impact to alter form. A close pass between two galaxies can tug at stars and gas, lifting them into long extensions and displacing the balance of a once orderly disk. Over time, one side may become stretched, an outer region may grow faint tails, or the central structure may become offset from the rest. Even if the companion later moves away or merges completely, the distortion can remain for a long time. In this way, a shape becomes a memory. The galaxy does not need to speak its history. Its structure already does. This makes unusual form especially powerful in astronomy, because it allows observers to infer long events from a single image. A ring galaxy offers one of the clearest examples of this principle. In such systems, the light is arranged not in sweeping arms, but in a circle that may surround a quieter centre. The symmetry can be so striking that it feels deliberate, almost artificial. Yet the ring is physical. It may arise when one galaxy passes through another and sends a density wave outward through the disk, compressing gas as it moves. That compression can trigger star formation in a growing circle, leaving behind a bright ring that marks the path of disturbance. The beauty of the form is part of what makes it so unsettling. A violent event can leave behind a shape that looks calm and composed. The galaxy holds together two opposite impressions at once. It appears elegant, but it may have been created by a profound disruption. Other galaxies seem lopsided rather than symmetrical. One arm may stand out while the other fades. One side of the disk may carry more mass, more star formation, or more dust. This can happen when material has been added unevenly, when a past encounter has shifted structure, or when the galaxy has not fully settled after disturbance. The imbalance matters because galaxies are often introduced as systems governed by orderly rotation and large-scale coherence. When that order is broken, the visible result is not mere mess. It is information about how fragile or how dynamic that order can be. A bent disk, a displaced core, or an uneven spread of light suggests that equilibrium has been challenged, and perhaps not fully restored. Some galaxies look as though their arms have been pulled loose. This appearance is especially striking in systems undergoing or recovering from close gravitational encounters. Spiral arms that in quiet conditions might remain broad and graceful can become elongated, frayed, or uneven. They may stretch into tails or bridges that reach away from the main body. The galaxy then appears less like a finished form and more like a structure still being worked on by outside force. The eye reads this immediately, even before the physics is understood. There is a sense of strain in the image. The shape looks as though it has been handled. That response, though emotional in tone, reflects something true about the underlying science. Gravity has acted across enormous distance and enormous time, reshaping the galaxy without needing to tear stars apart directly. Dust also plays a profound role in how galactic shape is perceived. A broad, bright body can appear suddenly more dramatic when a dark lane crosses it. Dust blocks and reddens light, which means parts of a galaxy can seem bruised, sliced, or hollowed depending on the angle of view and the thickness of the material. Sometimes the dust is part of a stable disk seen edge-on. In other cases, it may have been introduced or rearranged by merger and accretion. What matters is that a galaxy's visible form is not only made by stars, it is also made by what obscures stars. In this way, absence becomes part of shape. A dark band can define structure just as strongly as a luminous arm. The result can make a galaxy feel sculpted, wounded, or strangely layered. This helps explain why some of the most unforgettable systems owe their power not only to brightness, but to contrast. Light and shadow together tell the story. Strange galaxies refuse to stay in the background because their forms appear legible even across impossible distance. They look like aftermath, or interruption, or survival. They suggest that the universe does not build only with smooth repetition. It also bends, disturbs, scars, and rearranges. The more carefully these shapes are studied, the more they become readable as records of pressure, motion, and time. A galaxy is not a frozen ornament in space. It is a structure still responding to everything that has happened to it. In unusual galaxies, that truth rises closer to the surface. Their shapes are not merely different. Their shapes are testimony. The twisted disk, the bright ring, the wounded core, the stretched arm, and the uneven glow all reveal the same quiet lesson. Form in the universe is rarely innocent. It remembers. For a long time, galaxies were often described as though they moved along a fairly simple path. In youth, they were imagined as lively systems rich in gas, bright with blue light, and crowded with regions where new stars were still forming. Later, after much of that gas had been used or heated or driven away, they were expected to settle into quieter age. Their light would redden as older stars came to dominate. Their structure would remain, but their busiest days would be behind them. This broad picture still contains truth, yet the universe has proven less obedient than the model once suggested. Some galaxies that appear mature, settled, and far past their prime still manage to form new stars. Others seem to revive after long quiet periods. A system that looks finished from the outside may still hold the raw material for renewal, or may acquire it again from elsewhere. This is one of the reasons strange galaxies are so valuable. They show that galactic life does not always follow a single irreversible direction. Instead of moving cleanly from youth to retirement, a galaxy can stall, recover, and begin lighting new stars once more. The difference between a star-forming galaxy and a quiet one is often discussed in terms of gas. Stars are born when cold clouds of gas become dense enough for gravity to pull them inward until nuclear fusion begins. If a galaxy loses access to this cold material, star formation slows and can eventually decline to a very low level. Yet galaxies are not closed boxes. Gas can enter from outside. It can drift in from the surrounding environment, arrive through the capture of a smaller companion, or return to cooler form after having been heated and stirred. This means that even a galaxy with an old stellar population may not be truly finished. Beneath the calm light of older stars, there may still be reservoirs of material waiting for the right conditions. If compression occurs, if cooling becomes effective, or if new gas is delivered, a fresh round of stellar birth can begin. This creates one of the most interesting contrasts in galactic astronomy. A galaxy may look old and red overall, yet still contain pockets where bright young blue stars are forming. Those regions can appear as knots, rings, or scattered patches of renewal inside an otherwise mature system. The result is not simply visual variety. It is evidence that galactic evolution is more flexible than once assumed. A galaxy does not always retire on schedule. It may surprise observers by returning to activity after long quiet stretches. In some cases, this happens because of minor mergers. A smaller gas-rich companion can be drawn in and gradually absorbed. As it dissolves, it contributes fresh material to the larger galaxy. That gas may settle into the disk, fall toward the center, or become compressed in particular regions. Over time, this can reawaken star formation in a system that had appeared to be aging in peace. The event does not need to be spectacular from the outside. Even relatively small additions of gas can matter if they arrive in the right way. This is one more reminder that large systems can be changed by modest companions. Galactic history is often written through such unequal encounters. Other galaxies sustain star formation because their gas has not yet been exhausted, or because internal structure helps gather it into productive regions. Bars, spiral density waves, and rotating disks can all guide gas into lanes where compression becomes stronger. There, clouds can collapse, and star-forming regions can appear in arcs, bands, or rings. The galaxy then shows youth inside age, creation inside long continuity. What makes this especially fascinating is that the process does not erase the older history. A revived galaxy does not become young again in a simple way. It carries the light of ancient stars and the glow of new stars together. It becomes layered in time. The past remains visible, but so does the return of activity. This layering is one reason strange galaxies often feel richer than more textbook examples. They refuse to present a single clear stage of life. They contain evidence of multiple chapters unfolding at once. The distinction between blue active galaxies and red quiet galaxies is therefore helpful, but not absolute. Nature makes room for intermediate cases, transitional systems, and revived ones. Some galaxies continue star formation gently at a slow rate for vast spans of time. Others flare more noticeably after acquiring new gas. Some show rings of newborn stars around calmer interiors, suggesting that activity survives only in certain zones. In each case, the central point is the same. The life of a galaxy is not always a straight road. It can pause, it can divert, it can resume. This has important meaning beyond individual examples. It suggests that galactic evolution depends not only on initial conditions, but on later environment, repeated interaction, and the ongoing movement of matter through cosmic space. A galaxy is shaped not just by what it was born with, but by what it continues to encounter. Even silence in astronomy can be temporary. A system may seem dormant until fresh material arrives, and changes the balance once more. There is a quiet beauty in this idea. Vast structures that have existed for billions of years are not necessarily fixed in character. They may continue to respond, adapt, and reorganize. New stars can appear where calm once seemed permanent. A mature galaxy can still hold regions of beginning. This does not mean every quiet galaxy will return to activity, nor that renewal is always dramatic. In many cases it is partial, local, and limited. Yet even limited renewal matters. It shows that the visible stage of a galaxy does not always reveal the full range of what remains possible inside it. Strange galaxies make this lesson especially vivid because they blur categories that from a distance appear simple. The old division between youthful and aged systems begins to soften. What remains is a more interesting picture, one in which galaxies can keep changing far longer than expected. Their light becomes not a final verdict, but a current condition. Beneath that condition lies stored material, inherited structure, outside influence, and the persistent ability of gravity to gather matter into new stars. The galaxy that seemed finished may not be finished at all. It may only be waiting. When astronomers speak of colliding galaxies, the word collision can create the wrong picture. It sounds abrupt, violent, and crowded, as though countless stars are smashing directly into one another in a single catastrophic moment. The reality is both gentler in mechanism and grander in duration. Galaxies are immense systems in which the distances between individual stars are so vast that even when two galaxies pass through each other, direct star against star impact is extremely unlikely. What truly collides is the larger structure. Gravity pulls on every component. Gas clouds can compress, shock, and lose energy. Orbits are altered, disks are stretched, tails and bridges begin to form. The whole event unfolds not in a flash, but across millions and often billions of years. This is one of the reasons galactic encounters feel so strange. They are violent without being sudden, and destructive without resembling the kind of collision the human mind first imagines. Two galaxies may begin influencing each other long before they touch in any visual sense. As they draw near, each system starts to feel the changing gravitational pull of the other. The outer regions respond first. Stars and gas that once moved in relatively settled paths begin to shift. A spiral disk can become slightly distorted. Tidal forces, which arise because gravity pulls more strongly on the near side than the far side, begin to stretch the galaxy. These forces can draw matter outward into long arcs and narrow streams. Gas clouds may be compressed in some places and thinned out in others. The galaxies have not yet merged, and may still look distinct, but the argument between them has already begun. This early stage is part of what gives interacting galaxies their peculiar appearance. They often seem caught in the middle of a sentence that gravity has not finished writing. As the encounter deepens, the effects become harder to miss. One or both galaxies may develop tidal tails, luminous extensions of stars and gas pulled far from the main body. Bridges can form between the galaxies where matter has been drawn into connection. The original symmetry of a disk may give way to a warped or asymmetric outline. Dust lanes can shift. Star formation can increase where gas has been compressed by the disturbance. The system begins to look less like a settled island of stars and more like something under strain. Yet even this is not the final stage. In many interactions, the galaxies separate again after the first close pass, continuing onward for a time before gravity draws them back together. This is one of the most beautiful and disorienting features of galactic mergers. They are not single impacts. They are sequences of approach, passage, separation, and return. Each meeting removes a little more order from the original structure and transfers more energy into rearrangement. Over time, the pair loses the ability to remain apart, they fall back together and eventually surrender into one larger remade system. Because the process is so slow, astronomers observe different pairs at different stages and learn to read them almost like frames in a long unfolding record. Some systems show only gentle distortion. Others display spectacular tails and multiple bright cores. Others have blended so deeply that only careful study reveals that two galaxies once existed there. This range of appearances gives mergers a special place in astronomy. They turn time into visible shape. The strange galaxy with torn arms and extended tails is not simply damaged. It is occupying one chapter in a process that may last longer than human civilizations many millions of times over. The famous antennae galaxies offer a vivid example of this slow violence. Their long arcing tails of stars and gas extend far outward, while the main bodies remain entangled in ongoing interaction. The image is dramatic, yet it does not capture a single instant of impact. It captures a sustained gravitational encounter, one that has already reshaped both systems and is still moving toward eventual merger. What makes this so compelling is the contrast between the elegance of the forms and the severity of the forces behind them. The tails appear almost graceful, like luminous ribbons drawn through darkness, but each one records matter being pulled from its former orbit by immense gravitational strain. The beauty is real, but it is the beauty of disruption made visible. Gas responds especially strongly during galactic encounters because, unlike stars, gas clouds can collide, compress, and shed energy directly. This makes them especially important in shaping what happens next. When clouds of gas are driven together, they can trigger bursts of star formation. New stars may appear in the central regions where gas is funneled inward, or out in tidal debris where compressed material gathers and collapses. At the same time, some gas may be heated or driven away, affecting the future ability of the merging galaxy to continue forming stars. This means that collisions do not only distort shape, they influence the life cycle of the galaxy itself. They can ignite creation at the same time that they dismantle old structure. That dual character helps explain why interacting galaxies feel so rich in meaning. They are places where damage and renewal occur together. The final merged galaxy may look nothing like either original system. Spiral arms can disappear. Ordered rotation may give way to a smoother, more scrambled stellar distribution. The gas may become centrally concentrated, exhausted, or expelled. The result can resemble a more massive elliptical galaxy, though each merger outcome depends on the properties of the galaxies involved and the details of their encounter. What remains consistent is the lesson. Galaxies are not fixed architectural objects drifting unchanged through eternity. They are participants in a larger cosmic environment where gravity keeps drawing systems together and rewriting their forms over time. Strange galaxies make that lesson easier to see because they often catch the universe in the act of revision. The torn disk, the luminous bridge, the extended tail, and the doubled core all reveal that structure in the cosmos is not permanent. It can be stretched, argued over, and remade. A galactic merger is therefore not a sudden disaster, but a long transformation carried out with majestic patience. It is one of the clearest examples of how the universe combines violence with slowness, and how, over immense time, gravity can turn two separate worlds into one new and altered whole. Among the most unforgettable strange galaxies are those whose structures gather themselves into rings, wheels, and circles so precise that they seem almost too deliberate to be natural. In a universe often associated with turbulence, uneven growth, and violent interaction, these galaxies present a different kind of surprise. They do not first appear chaotic, they appear composed. A bright ring may surround a quieter centre. A near-perfect circular band of blue stars may float around an older yellow core. A galaxy may resemble a wheel with a rim, a hub, and hints of spokes. These forms are so clean that the eye almost distrusts them. They can look like illustrations, symbols, or design rather than the result of cosmic history. Yet they are real, and their very elegance is part of what makes them strange. They show that disturbance in the universe does not always leave behind jagged ruin. Sometimes it leaves behind geometry. A ring galaxy is one of the clearest examples of this. In broad terms, a ring galaxy is a system in which much of the visible light is concentrated in a circular band, often surrounding a less luminous interior. That ring may contain bright young stars, gas, and dust. While the central region appears calmer or older by comparison, the contrast alone is striking. Instead of the eye being led outward along spiral arms or into a central bulge, it is drawn around a circle. The galaxy seems to redirect attention into a narrow lane where much of the visible activity is concentrated. This already suggests that something unusual has happened to the normal arrangement of matter. The most widely accepted explanation for many ring galaxies involves collision. When a smaller galaxy passes through the disk of a larger one, especially near the center, the event can launch a density wave outward through the larger galaxy. This is not a solid wave like something moving through stone. It is a region of compression moving through stars, gas, and dust, somewhat like the expanding ripple produced when a stone strikes still water. As the wave travels outward, it compresses gas. Where gas becomes dense enough, star formation can ignite. The result is a bright expanding ring of young stars that marks the path of the disturbance. This is one of the most beautiful translations of violence into form that astronomy offers. A forceful passage through a galaxy can create a shape of startling clarity. The Cartwheel Galaxy is among the most famous examples. Its appearance strongly suggests the name. A bright outer ring forms the rim, while inner features hint at spokes and a more concentrated center. The image is so visually literal that it feels almost playful, yet the structure points to a serious history. Astronomers interpret the cartwheel shape as the aftermath of a smaller galaxy plunging through a larger disk system. The collision sent a wave racing outward, compressing material and triggering star formation in the ring. What makes the cartwheel so compelling is not only its form, but the way it captures time. The ring is not static decoration. It is the visible trace of an event still unfolding across immense scales. The outward moving pattern preserves the memory of impact, but in slow motion. It is like seeing the surface of a pond long after the stone has passed through. Except here, the pond is made of stars and gas, and the ripple spans tens of thousands of light years. Hoag's object offers a different kind of ringed mystery. It has one of the most improbable appearances in astronomy. At the center lies a round yellowish core of older stars. Around it, separated by a dark gap, is a nearly perfect blue ring where younger stars shine. The symmetry is so crisp that it can feel unreal at first glance. Unlike the Cartwheel Galaxy, which carries the marks of a more obvious disturbance, Hoag's object appears strangely composed and self-contained. Its dark gap makes the outer ring seem detached, as though the inner core and outer circle belong to different designs that somehow coexist. Astronomers still debate exactly how Hoag's object formed. One possibility involves a past interaction that reorganized the galaxy's material. Another explanation points toward internal processes that gradually shape the ring over time. What matters most in this context is not that the answer is final, but that the object resists simple explanation. It reminds astronomy that not every striking form can be reduced immediately to one settled story. Some galaxies remain strange, partly because their beauty is matched by uncertainty. Rings do not always arise in the same way. Some are formed by direct collision. Others may appear because internal structure channels gas into certain orbits. A bar within a galaxy, for example, can influence how gas moves through the disk, piling it up at particular distances from the centre. There, the material may become dense enough to produce a ring of star formation. In such cases, the ring is not the clear mark of an outside intruder, but the result of the galaxy's own internal dynamics. This broadens the meaning of circular structure. A ring is not one phenomenon with one cause. It is a visual form that can arise from different physical histories, which makes interpretation both richer and more demanding. What unites these galaxies is the way they reveal concentration. Instead of spreading activity broadly through the disk, they gather it into a circle. The eye reads this immediately as special. A ring feels chosen. It makes the galaxy look as though it has found one particular lane where change is still active, while the rest remains quieter. That contrast between centre and ring, calm and brightness, old stars and young stars, produces much of the emotional force of these systems. They seem ordered, but their order often comes from disturbance. They seem simple, but their simplicity is produced by complex history. Strange galaxies of this kind teach that the universe can create forms that look designed without requiring design. Gravity, motion, impact, and time are enough, under the right conditions. They can shape stars and gas into circles so striking that the mind pauses before accepting them as natural. Yet they are natural, and that is precisely what gives them their power. A galaxy can be torn, compressed, rearranged, and still emerge looking almost serene. The ring and the wheel are not exceptions to cosmic physics. They are some of its most elegant signatures. Some galaxies seem calm until their motion is studied closely. In an ordinary image, they may look balanced, settled, and entirely unremarkable. Their light appears smoothly arranged. Their disks seem coherent. Their centres do not obviously flare or twist. Yet when astronomers examine how stars and gas move inside them, a hidden strangeness can emerge. Material in one region may rotate in a different direction from material in another. Gas can orbit one way while stars closer to the centre move the other way. In some especially unusual systems, entire stellar components appear to be counter-rotating inside the same galaxy. This is one of the most subtle but powerful forms of galactic oddness, because it often cannot be seen by shape alone. The galaxy may wear a calm exterior while carrying a complicated internal history written in motion. To understand why this matters, it helps to begin with the ordinary expectation. In a relatively simple rotating galaxy, the stars, gas, and dust generally share the same broad sense of motion. They orbit the centre in a coordinated way, even if individual paths differ in speed and detail. This large-scale agreement reflects the way the system formed and settled over time. Material collapsing into a disk tends to preserve a common direction of angular momentum. The galaxy may contain bars, spiral arms, or small disturbances, but the overall rotation remains coherent. When astronomers discover a galaxy in which one major component moves against another, that coherence is broken. Something significant must have happened to create such a contradiction. Counter-rotation is therefore not merely a curiosity. It is evidence that the galaxy did not grow in complete isolation or remain untouched by outside influence. One likely explanation is that the galaxy acquired material from elsewhere. Gas drawn in from a companion or from the surrounding environment may arrive with a different direction of motion than the material already present. If that gas settles into orbit instead of being fully mixed at once, it can create a component that rotates opposite to the older stars. Over time, new stars may form from that acquired gas, preserving its direction of motion and deepening the internal complexity of the system. In this way, a past event that might leave little obvious mark on the overall shape can still remain clearly visible in the galaxy's kinematics, which is the study of motion. A galaxy then becomes like a quiet archive. Its light may look smooth, but its movement remembers. This is one of the most fascinating things about hidden motion in galaxies. A twist in shape can be striking to the eye, but a twist in motion can be even more informative. It suggests not only that something happened, but something about what kind of event it was. A minor merger, a long period of gas accretion, or repeated external feeding can all leave behind motion that refuses to align neatly with what came before. The visible body of the galaxy may appear serene because time has softened other signs of disturbance. Tails may have faded, bright starbursts may have ended, dust may have dispersed or settled. Yet the direction of motion can remain as a durable scar. Spectroscopy is what often reveals this hidden choreography. By spreading light into its component wavelengths and measuring slight shifts, astronomers can determine whether stars or gas in different regions are moving toward or away from the observer. From this, a map of rotation can be built. The result is often surprising. A galaxy that seemed quiet in broad light can become deeply strange when its internal movement is charted. One side of the disk may show gas approaching while the central stars suggest the opposite pattern. Or two stellar populations may reveal different rotational histories layered within one another. The galaxy then changes character completely. It is no longer just a shape in space. It becomes a record of multiple assemblies, each carrying its own inherited momentum. Counter-rotation also reveals something more general about how galaxies grow. They are not always assembled in one continuous sweep from a single isolated cloud. Many are built through addition, capture, and gradual transformation. A galaxy can swallow smaller companions. It can draw in gas from its surroundings. It can continue accreting matter long after its main structure appears settled. Each addition brings not only mass, but motion. If the new material arrives from an unfriendly angle or opposite direction, it may preserve that difference for a long time. This means that a galaxy's internal movement can be a history of acquisition. What appears as disorder is often a fossil record of how the system became what it is. There is a quiet elegance in this. The oddness is not random, it is structured memory. Some galaxies show even more subtle kinematic peculiarities. A central core may rotate differently from the outer body, not fully opposite, but misaligned by a noticeable angle. This can happen when the galaxy contains a kinematically distinct core, a region whose stars move in a pattern suggesting a separate origin or later restructuring. Such cores are especially interesting because they imply that the center itself may have been altered by merger or accretion. The innermost region of the galaxy, often assumed to be the most stable and ancient, may in fact preserve signs of later assembly. This turns the intuitive picture inside out. Stability at the center cannot always be assumed. Even deep in the heart of a galaxy, motion may reveal interruption. The broader lesson is that light alone can mislead. A galaxy may seem simple because its visible brightness is smooth, but simplicity of appearance does not guarantee simplicity of history. Strange galaxies repeatedly teach this. The true story may live not in outline, but in dynamics. Hidden motion expands the meaning of strangeness beyond rings, scars, and tails. It shows that the universe can hide its most revealing disturbances beneath a calm surface. The galaxy that looks undisturbed may in fact contain evidence of old mergers, borrowed gas, and layered structures moving past one another in silence. In this sense, the study of counter-rotation is not only about rare oddities, it is about learning to read galaxies more deeply. What seems serene may be complex. What seems orderly may contain contradiction, and what seems visually quiet may still be carrying an internal argument that gravity has not fully resolved. A strange galaxy does not always announce itself through shape. Sometimes it waits for motion to speak. One of the deepest reasons galaxies can seem strange is that much of what holds them together cannot be seen at all. Stars provide the obvious beauty. Dust shapes contrast. Gas can glow, drift, and collapse into new suns. Yet when astronomers measure how fast stars and gas move inside many galaxies, the visible material does not appear to provide enough gravity to account for what is observed. The outer regions often orbit too quickly. By ordinary expectation, they should not remain bound in the way they do. Their speed suggests that more mass must be present than telescopes can directly detect in starlight or glowing gas. This missing contribution is the foundation of one of modern astronomy's most important ideas. Galaxies are embedded in halos of dark matter, an unseen form of mass that does not shine, does not absorb light in the familiar way, and cannot be observed directly through ordinary imaging. Its presence is inferred through gravity. In this way, a galaxy becomes stranger the more carefully it is studied. The luminous structure admired in photographs may be only a bright trace inside a much larger invisible framework. This realization changes the way a galaxy is understood. At first glance, a galaxy may appear to be defined by what glows. Spiral arms seem to outline its true body. A bright bulge seems to mark its center of importance. A faint outer disk may appear to be the edge of the system, but motion tells a different story. If only the visible stars and gas were present, then objects farther from the center should move more slowly, much as planets farther from the Sun take longer and travel at lower orbital speed than inner ones. In many galaxies, however, the rotation does not decline in that way. Speeds remain high far beyond the brightest central regions. This suggests that a large amount of unseen mass continues outward, surrounding the visible galaxy in a vast halo. The galaxy is therefore not simply a shining object in space. It is a visible concentration suspended inside something much larger and mostly invisible. The ordinary eye would never guess this from appearance alone. That is part of what gives dark matter its strange power. It reveals how incomplete purely visual intuition can be. A galaxy can look light and airy, yet be held inside a massive dark structure that dominates its gravitational life. Some galaxies make this lesson especially vivid. Diffuse galaxies, low surface brightness galaxies, and ultra-diffuse galaxies often appear faint and insubstantial. Their stars are spread thinly over wide areas, and they can seem almost ghost-like against the dark sky. Yet, in some cases, measurements suggest that dark matter contributes an especially large share of their total mass. The visible stars are only a small luminous fraction of what is really there. This creates a remarkable mismatch between appearance and significance. A galaxy that barely announces itself in light may still be strongly bound, persistent, and dynamically important because of the unseen halo around it. The faint object becomes a lesson in humility. Brightness is not authority. What matters most in motion may not be what the eye first notices. The idea of dark matter also helps explain why strange galactic shapes can be so revealing. When galaxies interact, merge, or become distorted, their visible stars and gas respond to gravitational forces produced not only by one another's luminous matter, but also by their extended dark halos. Those halos overlap, tug, and help determine how the encounter unfolds. Tidal tails, warped disks, and other disturbances therefore carry information not just about the stars that can be seen, but about the hidden mass surrounding them. In this way, strange galaxies act almost like experiments performed by the universe itself. Their odd motions and distorted structures make the influence of invisible matter easier to infer. The dark component does not appear directly, but it leaves its signature in what visible matter does. It acts through consequence. A galaxy can therefore reveal absence as force. This is one of the great conceptual shocks of modern astronomy. The universe is not organized solely around luminous things. Much of its structure depends on something that does not take part in the visible pageant of light. Galaxies are among the clearest places where this becomes unavoidable, because their rotation and stability keep pointing toward the same conclusion. Without dark matter, many systems would not behave as they do. Their outer stars would not remain so tightly bound. Their extended forms would not endure so easily. Their interactions would unfold differently. The strange galaxy with unusual motion or unexpectedly large extent becomes especially useful because it highlights the tension between what is seen and what must be present. Dark matter halos are also thought to play a major role in the formation of galaxies in the first place. In the broad cosmological picture, dark matter begins gathering through gravity early in the history of the universe, creating regions where ordinary matter can later collect, cool, and form stars. This means that the visible galaxy may grow inside a pre-existing dark scaffold. The shining structure that later captures attention is built within a framework that never shines at all. Once again, the relationship between appearance and foundation is reversed. The part most visible is not the whole. It may not even be the deeper basis of the system. The deeper basis may be dark. This does not mean every detail of dark matter is understood. Its precise nature remains one of the major open questions in physics. Astronomers can describe how it behaves gravitationally and where it seems to be required, but they still do not know what particle or substance it ultimately is. That uncertainty does not weaken its importance for galaxies. On the contrary, it makes galaxies even more compelling as places where profound unknowns continue to shape observable reality. Every rotating disk, every faint halo, every disturbed merger and diffuse galaxy becomes part of the evidence. Strange galaxies matter especially because they exaggerate the mismatch between visible form and hidden mass. They show, sometimes more clearly than regular textbook examples, that the universe is full of structures whose true weight lies in what remains unseen. A galaxy can therefore be beautiful in a way that is incomplete, deceptive, and deeply informative all at once. Its stars and dust draw attention, but its motion tells the fuller truth. Beneath the luminous arcs and glowing cores lies a hidden architecture that does most of the holding. The galaxy turns in obedience not only to what shines, but to what does not. That is part of what makes these systems so haunting. They are built partly out of absence, yet the absence acts everywhere. The strange galaxy does not merely decorate the cosmos with unusual light. It reveals that invisible matter has been shaping cosmic form all along. Some galaxies become unforgettable not because they reveal a single dramatic process, but because their visible structures gather several unusual qualities at once: shape, dust, angle, and internal activity combine to create forms that seem almost theatrical from Earth, even though every feature arises from real matter moving through real history. In these galaxies, appearance becomes a powerful guide to underlying structure. A bulge may swell upward like the crown of a hat. A disk may narrow into an impossibly thin streak. A dark band of dust may bruise one side of the light. A long, narrow body may conceal violent star formation and outflowing gas. Each case reminds astronomy that a galaxy's character depends not only on what it contains, but also on how its material is arranged, and how that arrangement happens to face the observer. The strange galaxy is often not strange in only one way. It becomes memorable because multiple layers of physical meaning are compressed into a single image. The Sombrero Galaxy offers one of the clearest examples. From Earth, it appears dignified, balanced, and oddly dramatic at the same time. A brilliant central bulge rises strongly above a narrow disk, while a dark lane of dust cuts across the middle and gives the whole object its famous silhouette. The nickname is irresistible because the shape is so suggestive, yet the true fascination lies deeper. The bulge is unusually large and bright. packed with older stars that create a concentrated golden glow. Around it lies a thin disk containing dust that blocks light and sharpens the contrast between bright centre and dark lane. The result is a galaxy that appears halfway between familiar categories. It has something of a spiral structure, something of a more massive smooth system, and something distinctly its own. Seen from the right angle, the geometry becomes almost sculptural. This teaches an important lesson. A galaxy can owe much of its apparent personality to orientation. If the same system were viewed from another angle, its structure would read very differently. The strange impression comes partly from what the galaxy is, and partly from how it is seen. Needle galaxies extend this lesson even further. When a flat galactic disk is viewed edge-on, it compresses into a luminous line so narrow that it can seem unreal at first glance. A broad rotating system that might show graceful arms when seen face-on becomes a thin streak against darkness. Dust lanes become more prominent because they cut sharply through the flattened glow. Central bulges stand out above and below the disk like small thickenings in an otherwise narrow body. The entire galaxy seems transformed by angle alone. This is one of the quiet wonders of galactic astronomy. A small change in viewpoint can make a familiar type of structure appear entirely different. Needle galaxies reveal how flat many disks truly are in comparison with their enormous width. They turn galaxies into silhouettes, where depth and layering become visible not through brightness alone, but through the contrast between line, bulge, and shadow. Their strangeness is not caused by damage or exotic physics. It is caused by perspective, which makes them especially useful reminders that observation is always shaped by geometry. The Black-Eye Galaxy creates a different impression. What makes it so memorable is the sense of visible injury. One side of the bright central region is partly obscured by a thick dark band of dust, giving the object an appearance that really does resemble a bruised eye. The effect is dramatic, but it is not merely decorative. Dust consists of tiny grains mixed with gas, and it can block starlight so efficiently that parts of a galaxy seem cut away or shadowed. In the Black-Eye Galaxy, the uneven dust structure suggests a disturbed history. Astronomers infer that the system may have interacted with a smaller companion, or undergone a period of internal rearrangement that left its components mismatched. There is also evidence that not all of the material inside moves in one simple, coordinated way. This deepens the impression that the galaxy carries the mark of past complication. What is remarkable is how immediate the emotional reading can feel. A vast remote galaxy seems marked by a wound. This is not literally true in any biological sense. Yet the resemblance helps the human mind recognize that the structure is telling a story of disruption. Messier 82, often called the cigar galaxy, shows how a narrow visible shape can conceal intense internal turmoil. From our viewpoint, it appears long and compressed, a slim luminous body with a simple outline. But inside, the galaxy is undergoing a powerful starburst phase, meaning it is forming stars at a far higher rate than normal. This intense activity fills the system with massive young stars that shine fiercely, live briefly, and end in supernova explosions. Their combined energy pushes gas outward above and below the disk. In images, these outflows appear as glowing plumes and filaments, as though the galaxy is venting its own interior into surrounding space. The likely trigger for this frenzy is gravitational interaction with its neighbour, Messier 81, which disturbed the gas and helped ignite widespread star formation. What makes the cigar galaxy so compelling is the combination of compressed shape and expansive consequence. It looks narrow and contained, yet the processes inside it push material far beyond the disk. Creation and disruption unfold together. The same event that produces brilliant new stars also drives winds that can alter the galaxy's future. These named galaxies are memorable partly because they give astronomy a language of comparison: a hat, a needle, a bruised eye, a cigar. The nicknames may sound simple, but they do important work. They help observers remember that galaxies are not abstract smudges. They are three-dimensional structures with dust, orientation, internal activity, and layered histories. Each visible feature has a physical basis. The dust lane in the Sombrero Galaxy is real material blocking light. The thinness of a needle galaxy reflects a flattened disk seen sideways. The bruise of the Black Eye Galaxy is an uneven band of obscuring dust shaped by a disturbed past. The apparent narrowness of the Cigar Galaxy is a matter of angle. While the true drama lies in starburst activity and galactic wind, strange galaxies like these deepen the connection between visual form and physical meaning. They remind astronomy that what seems theatrical is still scientific, and what seems picturesque is often a compressed summary of structure, motion, and time. The universe does not merely produce galaxies, it produces appearances that can teach. In these remarkable nearby systems, shape is not a distraction from understanding. Shape is one of the clearest paths toward it. Some galaxies seem unable to choose between injury and radiance. Their forms suggest damage, their centers suggest appetite, and their surroundings carry signs of energy being pushed far beyond the regions where stars ordinarily shine. These are the galaxies in which wounds, bursts, and feeding cores appear together, making them feel less like settled stellar systems and more like ongoing consequences. They often reveal how several galactic processes can overlap at once. A merger may leave behind dust lanes and distorted structure. The same event may drive gas inward toward the center, where a supermassive black hole begins to feed more actively. At the same time, gas compressed elsewhere may ignite rapid star formation, producing short-lived massive stars and eventual explosions that stir the galaxy further. In such systems, nothing remains isolated. The scar, the central brightness, the outflowing material, and the reshaped body all belong to one connected history. This is one reason these galaxies feel so vivid. They do not display only one strange feature. They display several, woven together into a single visible record of consumption and response. Centaurus A is one of the clearest examples. At first glance, it appears to combine two different worlds. The larger body resembles a massive smooth galaxy, broad and bright in a way that suggests age and weight. Yet cutting across it is a thick, dark lane of dust and gas that looks completely out of place, as though another structure has been inserted into the system and never fully blended. That impression is close to the scientific interpretation. Centaurus A is widely understood to be the result of a merger in which a smaller spiral galaxy was disrupted and absorbed by a larger elliptical one. The dust and gas from the smaller system did not instantly vanish into the smooth body. Instead, they remained as a striking band, preserving the evidence of acquisition. The galaxy therefore looks wounded, but the wound is also a memory of growth. It tells the story of one system being consumed by another. The fascination deepens closer to the center. Centaurus A is not only a merger remnant, it also contains an active supermassive black hole that powers strong radio emission and enormous jets extending far beyond the visible galaxy. This means the same galaxy displays both the marks of swallowing and the marks of ignition. The consumed material may help feed the core, while the core in turn influences the environment through released energy. A quiet body crossed by dust would already be compelling. A dusty merger remnant with an active feeding heart becomes something richer. It seems altered in every direction. The past encounter remains visible in the lane of obscuring material. The present activity remains visible in the jets and radiation. The galaxy appears to be carrying two histories at once, one of disruption and one of extraordinary release. Messier 82 shows another kind of overlap between damage and brightness. Its narrow body already appears unusual from our angle, but the true drama lies in the starburst taking place inside. Massive young stars are forming rapidly, and with them come fierce radiation, stellar winds, and supernova explosions. These processes drive gas out of the galaxy in giant plumes that rise above and below the disk. In images, this gas can glow in red filaments and cloud-like streams, making it appear as though the galaxy is breathing fire into surrounding space. The event is not isolated from the galaxy's wider history. The starburst is thought to have been triggered by gravitational interaction with nearby Messier 81. Once again, outside disturbance and internal consequence are linked. A close encounter reshapes the gas. The gas ignites rapid star formation. The new stars then flood the galaxy with energy and begin to blow material outward. Creation does not arrive alone, it arrives entangled with loss. This combination makes starburst galaxies especially revealing. A burst of star formation sounds gentle in name, but physically it involves intense compression, short lifetimes for massive stars, repeated explosions, and large-scale changes in the gas that future generations of stars would otherwise depend on. The galaxy shines with youth while also spending itself rapidly. It is full of beginning, but the beginning is fierce enough to alter what comes later. That dual quality gives systems like Messier 82 their unusual emotional force. They feel alive with consequence. Nothing inside them is resting. The same broad principle applies to galaxies with active cores that feed strongly enough to transform their surroundings. Gas driven inward by merger, bar structure, or general instability can accumulate near the central black hole. As the black hole feeds, energy is released in the disk around it and sometimes in jets or winds moving outward. This energy can heat surrounding gas, disturb it, or prevent it from cooling into new stars. The core then becomes both luminous and regulatory. It is not just consuming matter, it is changing the conditions of the entire galaxy. This is another way wounds and feeding become connected. The disturbance that channels gas inward may leave visible scars. The feeding that follows may then help determine whether the galaxy continues vigorous star formation or becomes quieter later on. In this sense, the strange galaxy is not a collection of unrelated oddities. Its visible features participate in one process chain: dust lanes, bright nuclei, winds, jets, and bursts of young stars are different expressions of matter being moved, concentrated, heated, and expelled. Even the appearance of injury can become scientifically fruitful. A dust scar marks where obscuring material lies. That material may have arrived through merger. If enough of it falls inward, it can help power central activity. If it's compressed elsewhere, it can form new stars. If energy from those stars or the active core pushes it back out, the galaxy acquires plumes, filaments, and long-term change in structure. The scar is therefore not passive. It may be part of the same reservoir that fuels later brilliance. This is what makes certain strange galaxies feel so complete in their strangeness. They tell stories in which every visible feature belongs to one broad cycle of disruption and response. The wounded galaxy is often the feeding galaxy. The feeding galaxy is often the bright galaxy. The bright galaxy is often the one driving material outward again. From a distance, such systems may still appear as beautiful forms suspended in dark silence. Closer study reveals something far more dynamic. The galaxy has been altered by encounter, filled by inflow, ignited at the center or across the disk, and made to shed energy into space. It becomes a place where gravity gathers, compression creates, and release transforms. Strange galaxies of this kind show that calm appearances can hide vast internal consequence, and that the marks of disturbance are often inseparable from the marks of power. A close encounter between galaxies can leave behind some of the most elegant signs of disturbance in the universe. Matter that once moved in settled orbits around a galactic center can be pulled outward into long streams, narrow bridges, and faint extensions that seem to write motion across the dark. These structures are known as tidal tails and bridges, and they form when gravity reaches into a galaxy and begins to rearrange its outer regions during a near-pass or merger. What makes them so remarkable is that they combine visual grace with physical violence. A tail can curve through space like a ribbon of dim light. A bridge can stretch between two galaxies like a temporary road connecting separate worlds. Yet each of these features is evidence that the original balance of the system has been deeply disturbed. The stars and gas did not wander into those shapes by chance. They were pulled there by differential gravitational forces acting across enormous distance and enormous time. In this way, galactic encounters turn motion itself into visible calligraphy. The term tidal refers to the same basic idea that causes tides on Earth, though on a scale almost beyond imagination. Gravity pulls more strongly on the near side of a galaxy than on the far side when another massive system approaches. This difference in pull stretches the galaxy. The effect is especially strong in the outer regions, where stars and gas are held more loosely than material deep near the center. As a result, matter can be drawn outward into extended tails. Sometimes one tail forms more prominently than another, depending on the orientation of the encounter and the structure of the galaxy involved. In other cases, both galaxies grow long tails, giving the whole system an appearance of unraveling. These tails can extend for extraordinary distances, far beyond the compact luminous body that first defined the galaxy. They are not tiny distortions. They are major restructurings of visible matter. This is one reason they feel so dramatic. A galaxy is not merely bent. Part of it is being pulled out into the open. Bridges form under related conditions. During a close interaction, material from one or both galaxies can be drawn into the region between them, creating a luminous connection. A bridge is therefore not a solid beam in any engineered sense. It is an extended structure of stars and gas produced by shared gravitational distortion. It shows that the encounter is not only pulling matter away into isolation, but also redistributing matter into connection. The result can make two galaxies appear linked in mid-passage, as though the space between them has become a place of temporary architecture. That impression is powerful because it captures something true. During these encounters, the galaxies are not separate in the way they once were. Their outer regions have begun to overlap dynamically. Each system is reaching into the other. A bridge is the visible expression of that reach. Tidal tails and bridges are not important only because they are beautiful. They preserve information. Their length, curvature, brightness, and direction all depend on the masses of the galaxies involved, the angle and speed of approach, and the stage of the interaction. In that sense, they are readable traces of an event. Astronomers use them to infer what kind of encounter took place and how far it has progressed. A long thin tail suggests a strong but not fully destructive pull on the outer disk. Multiple tails can imply a particularly effective tidal exchange. A bridge can indicate that the two galaxies have passed close enough for matter to be shared or stretched between them. These features become a historical record, one written not in words but in redistributed light. The galaxy does not need to retain its former symmetry to remain intelligible. In some ways, it becomes more intelligible after distortion, because the forces acting on it are easier to see. The Tadpole Galaxy is a particularly vivid example. Its nickname comes from the long, luminous tail extending from the main body, giving the entire system a shape that feels alive with motion. The tail was created not by movement through empty space in the way the name might suggest, but by gravitational interaction with another galaxy. As the two systems passed near one another, stars and gas were pulled outward into an extended stream. Within that tail, bright blue star clusters formed, adding new points of brilliance to what might otherwise have seemed like debris alone. This is one of the most striking aspects of tidal structures. They are not merely leftovers. They can become places where new structure appears. Material torn loose from a galaxy can still collapse locally and form stars. The tail then becomes both scar and nursery, both evidence of loss and site of beginning. This dual role makes tidal features especially compelling. They embody one of the recurring truths of strange galaxies, which is that disruption and creation often occur together. A galaxy can be damaged in one sense while becoming newly active in another. Matter drawn out of stable orbit is not always rendered useless. It may glow faintly as a record of what happened, or it may compress into clusters that continue the story in a new form. The tail therefore becomes more than a sign of what has been taken away. It becomes a place where the future is also being shaped. This helps explain why these structures feel so emotionally resonant even in scientific images. They look like loss, but not only loss. They look like aftermath, but not only aftermath. They hold continuation inside disturbance. Tidal tails also demonstrate that galaxies are far less self-contained than they first appear. In a quiet image, a galaxy can look like an isolated island of stars, bounded by its own light and finished in its own outline. During interaction, that illusion dissolves. Gravity reaches outward, and the edges become porous. The outer stars and gas can be drawn far away, redistributed into streams, and woven into patterns that no longer respect the original shape. The galaxy begins to exceed itself. It extends into the surrounding dark in a way that makes its former boundary seem temporary. Strange galaxies often reveal this best, because they show the universe in the act of rearranging structure rather than preserving it. A tail or bridge is therefore more than a strange appendage. It is a visible argument against the idea of the galaxy as a fixed, finished form. Instead, it presents the galaxy as something responsive, vulnerable, and unfinished. Under the influence of another massive neighbour, even a large settled system can be stretched into long, calligraphic traces across space. The resulting beauty is not separate from the physics. It is the physics made visible. Tails and bridges show gravity acting not as an abstraction, but as a sculptor that works slowly, reaches widely, and leaves its marks in light. Not every galaxy offers the sweeping elegance of spiral arms or the calm balance of a smooth elliptical glow. Some resist these familiar patterns almost completely. Their stars appear scattered unevenly. Their bright regions are clumped rather than ordered. Their bodies seem rough, bent, or unfinished, as though gravity has been working on them without ever allowing them to settle into symmetry. These are the irregular galaxies, along with other systems that seem to live outside the neat visual categories that textbooks first present. What makes them so compelling is not simply that they look disorderly. It is that their disorder often carries meaning. A galaxy without graceful structure is not necessarily primitive, failed, or incomplete in any simple sense. It may instead be a system shaped by repeated interaction, by the pull of nearby companions, by unequal growth, or by conditions that never allowed a stable disk and clear spiral pattern to dominate. In these galaxies, the absence of symmetry becomes its own kind of evidence. The familiar spiral galaxy is memorable because its shape seems to promise order. The arms curve outward in luminous rhythm. Gas, dust, and stars settle into a form that the eye quickly reads as coherent. But this structure depends on conditions. A galaxy needs the right balance of mass, motion, gas, and internal dynamics to sustain such patterns. If those conditions are disrupted, the result can be very different. A close encounter with another galaxy can tug material out of ordered paths. A small system may never gather enough mass or angular momentum to form a large stable disk in the first place. Repeated gravitational harassment in a busy environment can prevent long-term symmetry from emerging. Gas can be stirred unevenly, star formation can become patchy, and the visible body can take on a lopsided or fragmented appearance. The irregular galaxy therefore reminds astronomy that order is not guaranteed. Structure is something earned, maintained, or sometimes lost. The Large Magellanic Cloud and the Small Magellanic Cloud, which orbit near the Milky Way, are among the best-known examples of irregular galaxies. They do not present the sweeping ordered design of a grand spiral. Instead, they show a more uneven and disrupted visual character, with patchy bright regions and asymmetrical distribution of stars and gas. Their forms are not accidental. They're shaped by their relationship with each other and with the Milky Way. This is one of the most useful lessons irregular galaxies provide. Chaos in astronomy is often relational. A galaxy may look misshapen, not because it somehow failed to form properly in isolation, but because it has spent its life in company. Nearby mass matters. Repeated gravitational influence matters. The visible result is a kind of record of companionship, though it is companionship expressed through distortion rather than harmony. There is a quiet honesty in these galaxies. They do not hide the fact that they have been acted upon. Their asymmetry sits near the surface, easy to see even before detailed measurements begin. Bright star-forming regions may lie off-center. The body of the galaxy may look stretched in one direction and compressed in another. Dust and gas may appear unevenly distributed, and no simple rotational elegance may unify the whole. This visible roughness can make irregular galaxies seem less graceful than classic spirals, but that judgment says more about human expectation than cosmic value. In physical terms, these galaxies are often deeply informative. They show what happens when gravity keeps working on a system without allowing it to become visually serene. They preserve the signs of disturbance in a more open form. This makes them feel less like completed islands of stars and more like ongoing events. Some irregular galaxies are relatively small, and their low mass makes them especially susceptible to outside influence. A large spiral or elliptical galaxy possesses deeper gravitational binding and can sometimes absorb disturbance without losing all recognizable structure. A smaller galaxy may be pushed, stretched, or compressed much more easily. Its gas may be displaced. Its star-forming regions may become concentrated in odd places. Its overall form may lose coherence more readily. This does not make it less interesting. On the contrary, it means that small irregular galaxies can become sensitive traces of galactic environment. They respond visibly to forces that in a larger system might leave subtler marks. Their roughness becomes diagnostic. Through them, astronomers can study how interaction, tidal influence, and environmental pressure shape structure over time. Not all galaxies without neat spiral arms are classified as irregular in the strictest sense, but many still challenge expectation in related ways. Some systems look boxy, smooth, or undefined rather than beautifully curved. Others may have once possessed more ordered forms and later lost them through collision or merger. A galaxy can therefore become strange not only by never developing a classic pattern, but by having one disrupted or erased. This broadens the meaning of irregularity. It is not a single family of appearances. It is a reminder that the visual language of galaxies is more varied than any one set of ideal examples suggests. Once this is accepted, the sky becomes richer. The absence of symmetry stops looking like a deficiency and starts looking like a clue. Irregular galaxies also help disentangle the idea that beauty in astronomy must come from order. There is another kind of beauty in these systems, one grounded in process rather than perfection. a lopsided spread of starlight, a handful of bright knots scattered through a diffuse body, an outline that refuses to settle into a familiar curve. All of these can be read as signs that gravity has remained active and unresolved. The galaxy is not static. Its present form is a temporary state inside a longer history of pulls, losses, bursts, and adaptation. In that sense, irregularity is not emptiness of design. It is design continually interrupted. Strange galaxies of this kind reveal how little the universe owes to neat symmetry. A galaxy does not need graceful arms to contain meaning. It does not need a balanced profile to preserve history. It may carry its story most clearly in unevenness, in clumps, in displaced light, and in the visible refusal of matter to settle into something simple. These galaxies expand the imagination because they show that the cosmos is not arranged according to human preference for order. It is arranged according to gravity, motion, environment, and time. When those forces do not cooperate toward elegance, they still produce systems worthy of attention. The irregular galaxy stands as proof that roughness can be revealing, and that some of the clearest records of cosmic influence are written not in harmony, but in a symmetry. The largest galaxies in the universe often appear commanding, self-contained, and dominant. Yet some of their most important changes come from much smaller companions. Dwarf galaxies contain far fewer stars than major spirals or ellipticals, and from a distance they can seem almost minor by comparison. They are fainter, less massive, and easier to overlook. But over cosmic time, these small systems can leave effects vastly out of proportion to their size. When a dwarf galaxy falls toward a larger one, gravity can begin tearing it apart long before the process is complete. Its stars may be stretched into long streams, its gas may be stripped away, its dark matter halo may be disrupted and absorbed. The dwarf does not simply vanish, it is redistributed. In being consumed, it can reshape the larger galaxy that swallows it. This is one of the great lessons of strange galaxies and of galactic history more broadly. Importance in the universe is not always tied to scale. The smaller partner can become unforgettable precisely because it is taken apart and spread through something larger. A dwarf galaxy entering the gravitational field of a major galaxy experiences powerful tidal forces. The near side is pulled more strongly than the far side, and the difference begins to stretch the smaller system. If the orbit brings the dwarf repeatedly through the outer regions or halo of the larger galaxy, more and more of its material can be stripped away on each pass. Stars drift into long tidal streams. Gas can be removed and added to the larger galaxy's supply. Dark matter from the dwarf becomes harder to distinguish, as its halo is disrupted and mixed into the broader invisible framework surrounding the host. This is not usually a quick dramatic event. It is a slow transfer, carried out over many orbits and vast spans of time. The dwarf may survive for a while as a recognizable object even while leaving behind trails of itself. That makes these systems especially compelling. They show growth as an ongoing process of accretion rather than a single decisive act. The larger galaxy feeds gradually, and the meal itself becomes part of the visible architecture. Stellar streams are among the clearest signs of this process. These long ribbons of stars trace the path of disrupted dwarf galaxies around their hosts. They arc through the halo like pale memories of something once more compact. To the eye, they can look delicate, almost decorative, but they are physically important. Each one marks where a smaller system has been pulled apart and redistributed by gravity. The stream preserves information about the dwarf's orbit, its mass, and the gravitational field of the host galaxy. In this way, what seems like leftover debris becomes a tool for understanding structure on a larger scale. The larger galaxy is not merely collecting ornament, it is being built, The outer halo, the thickness of the disk, and even aspects of the central structure may all be influenced over time by the repeated accretion of small companions. This means that major galaxies are often archives of many minor encounters. Their grandeur is partly assembled from the remains of smaller worlds. The Sagittarius dwarf galaxy offers one of the most vivid nearby examples. It is currently being torn apart by the Milky Way, and its stars are spread into streams that wrap around our galaxy. This makes the process feel less abstract. The destruction of a small companion is not only something that happens in remote images of distant systems, it is part of the continuing history of the galaxy that contains the Sun. The Sagittarius streams show that galactic growth can still be happening in the present era, and that a dwarf companion can leave marks visible across enormous regions of the sky. These are not mere leftovers of a completed event. They are active evidence that accretion is ongoing, that gravity is still at work, and that even a galaxy as vast as the Milky Way continues to be shaped by smaller arrivals. What makes this especially striking is the mismatch in scale. The dwarf itself may contain only a tiny fraction of the stars in its host, yet once stretched along its orbit, it can leave traces across distances so large that the original size difference begins to feel less decisive. The consumed system becomes spatially enormous in its afterlife. In that sense, being torn apart makes the dwarf more visible in certain ways, not less. It ceases to be a compact object and becomes a pattern written across the host's outskirts. This reversal gives dwarf accretion much of its strange power. The small galaxy matters not despite being consumed, but partly because consumption spreads its influence so widely. Dwarf galaxies also remind astronomy that the history of large galaxies is not only a history of major mergers between near equals. Much of galactic growth happens through repeated minor mergers, each one smaller, quieter, and easier to miss in isolation, but transformative when accumulated across billions of years. A single dwarf accretion event may alter the outer halo or add a stream. Many such events over time can build substantial components of the host galaxy. The thick disk may preserve evidence of old heating and added stars. The halo may consist in part of remnants from long-absorbed companions. Even chemical signatures in stars can reveal that some populations formed in smaller systems before being incorporated into the larger one. The giant galaxy therefore becomes composite in a deep sense. It is not one uninterrupted lineage, but a gathering place for many lesser histories. There is a particular beauty in the patience of this process. A dwarf galaxy can orbit, lose material, return, and lose more again, each pass giving part of itself to the larger system. Growth happens in stages. The host gains mass and complexity while the dwarf becomes less a single object and more a distributed memory. Strange galaxies often make this visible through streams, asymmetries, and faint external structure. But the principle reaches far beyond obviously peculiar systems. Many galaxies that appear calm today may owe part of their present form to ancient dwarf companions now completely dissolved. The lesson is both humbling and expansive. Size alone does not decide significance. A small galaxy can alter the course of a great one. It can feed it, reshape it, and leave behind structures that outlast its own integrity. In the universe, the difference between major and minor is not always the difference between important and unimportant. Sometimes the smaller partner becomes central to the larger story precisely by being absorbed into it. The strange galaxy, read carefully, often carries these traces in plain view: long arcs of stars, uneven outskirts, and persistent kinematic clues all reveal that small companions have been helping build the grandest systems all along. Some of the strangest galaxies are not the ones that blaze most brightly, but the ones that seem to hover at the edge of visibility. They do not command attention with sweeping arms, brilliant cores, or strong contrast. Instead, they appear faint, diluted, and nearly absent, as though the universe has chosen to build a galactic structure and then withhold most of the light that would normally announce it. These are the ghostly systems diffuse galaxies, ultra-diffuse galaxies, dark galaxy candidates, and low-surface brightness galaxies. What unites them is not that they are all the same kind of object, but that they challenge one of the most instinctive assumptions in astronomy, which is that importance should be easy to see. In these galaxies, the opposite may be true. A system can be large, massive, and dynamically real while remaining visually understated. The eye expects galaxies to declare themselves. These galaxies whisper and sometimes almost disappear. A diffuse galaxy spreads its stars so thinly across space that the light becomes faint and hard to notice. The stars are present, the structure is present, and the history is present, but the brightness is diluted over such a wide area that the whole object can seem insubstantial. Against the darkness of space, it may appear as little more than a weak smudge. Yet this faintness does not mean the galaxy is unreal or unimportant. It means the light is distributed differently from the denser, more easily recognized systems that dominate familiar images. This alone is enough to make diffuse galaxies deeply instructive. They reveal that visibility depends not only on total light, but on how concentrated that light is. A galaxy can be substantial and still evade notice if it shines too softly over too large a region. In this sense, some galaxies do not hide behind exotic curtains. They hide through understatement. Ultra-diffuse galaxies take this idea even further. Some are comparable in overall size to the Milky Way, yet they contain only a small fraction of its stars. This mismatch between scale and brightness is what makes them so remarkable. A galaxy with such a broad spread of stars might be expected to look more commanding, but instead it can appear fragile and nearly transparent. In crowded galaxy clusters, their survival becomes even more intriguing. Those environments are full of gravitational stress, close passes, and disruptive influence, conditions in which such delicate-looking systems might be expected to fall apart, yet some persist. Astronomers are still working to understand how they formed and why they endure. Some may have lost gas early and therefore failed to build many stars. Others may sit inside unusually massive dark matter halos that help hold them together despite their sparse visible populations. Either way, they expand the imagination. They make the universe seem capable of constructing galaxies with far less light than familiar examples would lead one to expect. Dark galaxies represent an even stranger possibility. In principle, a galaxy could exist as a gravitational structure rich in gas and dark matter, but with little or no star formation to light it up in visible wavelengths. Such a system would be difficult to detect because stars are usually what first announce the presence of a galaxy. Without starlight, the object would remain nearly invisible in ordinary optical observation. Astronomers search for such candidates indirectly by looking for hydrogen gas, unusual motions, or effects on nearby visible systems. The very idea is startling because it challenges the way galaxies are mentally defined. The usual image is a city of stars. A dark galaxy would instead be more like a hidden framework, a galactic body without the luminous display that usually accompanies it. Whether every candidate fully fits that picture remains uncertain, but the concept itself matters. It suggests that the universe may build large-scale structure without always lighting it in a way human eyes immediately recognize. Low-surface brightness galaxies occupy an important place in this wider family of faint presences. Surface brightness refers to how much light comes from a given area. A galaxy can therefore have a respectable total amount of light and still remain difficult to notice if that light is spread too thinly across the sky. Such galaxies may sit in survey images for years without attracting much attention, especially when brighter objects nearby dominate the field. This makes them fascinating in a very particular way. They are not hidden because they are impossibly distant. They are hidden because they do not insist on being seen. Once discovered, many prove to be rich in gas and dark matter, with relatively modest star formation and slower apparent evolution than more dramatic systems. They feel like the quiet underclass of galactic life, present all along, but easily ignored. Strange galaxies of this kind force astronomy to reconsider what counts as presence. A galaxy can be real, massive, and influential while remaining faint enough to seem almost absent. It may bend the motions of nearby matter, persist for billions of years, and preserve a long history, all while barely registering in ordinary images. This is one of the most haunting lessons of the ghostly galaxies. The universe is not arranged according to what most easily catches human attention. What looks important and what is important dynamically can be very different things. The bright spiral and the faint diffuse smudge may both be significant, but only one is likely to be noticed first. The faint one waits for patient instruments and patient interpretation. There is also a philosophical shift in these systems. Bright galaxies give the impression that the cosmos is generous with spectacle. Faint galaxies suggest something more secretive. They imply that much of the universe may remain understated, and that discovery is not always a matter of looking farther, but of learning to notice what is already near enough yet too softly lit to stand out. The sky may contain more hidden structure, not because it is impossible to reach, but because it is easy to overlook. This makes ghostly galaxies especially resonant. They do not only add new members to the catalogue of strange things, they change the rules of attention. They reveal that a galaxy does not need to blaze to matter. It may survive in near silence, with stars spread thinly, or with gas and dark matter doing most of the structural work. It may be large but faint, present but nearly invisible, massive but visually modest. Such systems widen the idea of what a galaxy can be. They teach that the cosmos contains not only dazzling architecture, but also delicate frameworks that haunt the edge of sight. In them, strangeness comes not from violent appearance, but from the unsettling fact that so much can be there while seeming to be almost nothing at all. The strangest galaxies do not belong only to the remote universe. They also leave traces much closer to home, written into the structure of the Milky Way itself. From the inside, our galaxy can be difficult to judge as a whole. Human observers live within its disk, surrounded by dust, stars, gas, and local perspective. This makes the Milky Way feel familiar in a way no outside galaxy can. It is the sky of home, the broad river of starlight that cultures have named for thousands of years, and the galactic system that contains the sun, the planets, and every known human story. Yet when astronomers study it carefully, the Milky Way begins to resemble the very galaxies that elsewhere seem odd, disturbed and historically layered. Its calm appearance hides evidence of old mergers, torn companions, stellar streams, and structural components that likely form through repeated accretion. The lesson is quiet, but profound. The history of strange galaxies is not only the history of rare objects far away, it is also part of the history of the galaxy in which this story is being read. One of the clearest signs of this is the presence of stellar streams in the galactic halo. These long arcs of stars move through the outskirts of the Milky Way as remnants of smaller systems that were pulled apart and absorbed. They are not random scatterings. They are coherent traces of past accretion, just as tidal tails and streams in distant galaxies preserve evidence of interaction. From our position inside the Milky Way, these streams do not always announce themselves as dramatic visible structures in the same way that external galaxies do in photographs. Instead, they emerge through careful mapping of stellar positions, motions, and chemical signatures. When revealed, They show that the halo is not a featureless sphere of ancient stars. It is patterned with memory. Some of that memory belongs to dwarf galaxies that once orbited independently and then gradually unraveled under the Milky Way's gravity. The Sagittarius dwarf galaxy is the most famous living example. It is being disrupted even now, and its stars wrap around the Milky Way in great streams. This makes the process of galactic feeding immediate rather than purely historical. Our own galaxy is still growing through accretion, still reshaping smaller companions, and still carrying the evidence in structures spread across the sky. The thick disk and the stellar halo may also preserve the effects of earlier mergers. Stars in these regions can differ from those in the thin disk, not only in their orbits, but in age, composition, and dynamical history. Some populations appear to have been heated by ancient encounters that disturbed the Milky Way's older structure. Others may have originated in absorbed systems and later become part of the broader galactic body. This suggests that even what seems fundamental in the Milky Way may be composite. The galaxy is not simply one uninterrupted structure built in isolation. It is a layered system assembled through both internal evolution and outside addition. This aligns the Milky Way with the larger story told by strange galaxies elsewhere. The warped disk, the accreted streams, the swallowed dwarfs, and the mixed stellar populations all suggest that our galaxy has not lived a quiet, solitary life. It has been shaped by company, by gravity, and by time. Another important shift comes from perspective. When strange galaxies are viewed from afar, their oddities often appear all at once. A ring stands out immediately. A tidal tail can be seen in a single image. A dust lane cuts across the light in a way the eye reads at once. The Milky Way does not offer that simplicity because it surrounds the observer. Its strangeness has to be reconstructed rather than merely seen. Astronomers must combine measurements of individual stars, motions, distances, and compositions to infer the larger pattern. In some ways, this makes the Milky Way even more intimate as an example. Its oddness is not presented as spectacle. It is discovered patiently, detail by detail, until the familiar galaxy of home begins to reveal the same kind of turbulent inheritance that elsewhere appears more obviously dramatic. This inversion is deeply beautiful. The galaxy that once seemed like the quiet standard against which other strange systems were compared turns out to contain many of the same signatures. It too has been fed by smaller companions. It too has streams in its halo. It too has likely been bent, heated, and reshaped by ancient interactions. The Milky Way therefore changes the emotional meaning of strange galaxies. They are no longer just remote exceptions. They become mirrors, helping us understand that our own cosmic setting belongs to the same universe of merger, accretion, disturbance, and renewal. The home galaxy is not outside the story, it is inside it. This also softens the idea that there is a sharp division between ordinary galaxies and strange ones. The more deeply a galaxy is studied, the more layered its history tends to become. Some systems display their strangeness openly through rings, scars, or dramatic tails. Others hide it in motion, in faint outer structure, or in the chemistry of stars. The Milky Way shows that even a galaxy that appears broadly orderly can still carry the marks of a complicated past. That recognition helps gather the themes of strange galaxies into one final view. Active hearts, warped shapes, collisions measured in ages, rings born of impact, hidden counter-rotation, invisible dark matter, bright starbursts, tidal tails, irregular forms, dissolving dwarfs, and ghostly systems at the edge of sight all point toward the same larger truth. A galaxy is never just a still arrangement of stars. It is an evolving record of forces acting across immense time. The strange cases make that truth easier to notice, but they do not create it. They simply reveal it more clearly. In the end, the Milky Way stands not apart from that revelation, but within it. Our own galaxy carries memory in its halo, change in its structure, and evidence that even home is built from encounter. The strangest galaxies alter how the universe is seen because they teach that calm appearance is often only the surface. Once that lesson is learned, every galaxy, including this one, begins to look deeper, older, and more alive with history than it first appeared. The long survey of strange galaxies now settles into a quieter view. The brightest rings, the torn tails, the feeding black holes, the ghostly faint systems, and the swallowed companions all begin to feel less like separate curiosities and more like variations on one calm truth. A galaxy is never only what it first appears to be. Light shows part of the story, but motion, hidden mass, old encounters, and patient change continue beneath the visible surface. What seems serene may contain violence softened by time. What seems chaotic may preserve an underlying order shaped by gravity. What seems faint may still hold great weight. Across the universe, these vast systems drift through ages of growth, collision, renewal, and loss, carrying their histories in rings, scars, streams, dust, and silence. Even the Milky Way joins this pattern, holding within its own structure the memory of ancient arrivals and unfinished change. The strange galaxy and the familiar galaxy begin to draw closer together, until the difference between them is no longer absolute. Each one becomes a record of the cosmos learning how to arrange matter, disturb it, gather it again, and leave traces that can still be read across immense distances of space and time. The mind can rest with that thought. The universe does not rush. It turns slowly, feeds slowly, merges slowly, and remembers slowly. In that great patience, galaxies continue their quiet transformations, shining where they can, fading where they must, and carrying the hidden architecture of the cosmos through the dark,